Hi, everyone. Welcome to our talk about near-stream computing, general and transparent near-cache acceleration. In modern processors, data movement have become an increasingly challenging bottleneck. This is largely because conventional systems are core-centric. They first fetch all the data to the core, perform the operation, and then write back the result. This data movement problem becomes more severe as systems scale up. While prefetching can partially help to reduce the latency and the request traffic, it does not reduce data movement. To tackle this problem, architects proposed near data computing to decentralize the computation. Such approaches offload computation to different locations in the system with various technologies. In this work, we focus on offloading to shared last level cache, the LLC, since many algorithms are blocked or tied to use LLC, and its capacity has been increasing rapidly in recent designs, making it even more useful. Our key observation is that existing NDC techniques fail to fully cover the triangle of transparency, synchronization efficiency, and generality due to their inappropriate choice of NDC offloading abstraction, be it instructions, user-defined functions, or threads. A common offloading abstraction is thread context. It does provide transparency and synchronization efficiency, but is too coarse-grained and only works best with a single data structure. The other extreme point is to offload a short sequence of a couple of instructions. It can be very flexible and thus provides transparency and generality. However, it is too fine-grained and sacrifices synchronization efficiency, as it takes at least one request per operation. Some works also offload user-defined functions. It usually requires manual programming and thus breaks transparency. It does provide synchronization efficiency and generality, but at the cost of sequential semantics. So the key research question here is, can we find a practical abstraction that is general, efficient, and program transparent? Our solution is to use streams as the new abstraction for NDC. A stream can be defined as an address generation sequence that can be decoupled from the program. They are prevalent in data processing workloads. For example, here we have two load stream and one store stream C. More importantly, streams capture long-term access patterns of each data structure and expose rich information for transparent and general offloading. With these insights, we propose near-stream computing, in which streams are offloaded to the level of memory hierarchy that provides the best locality, and the computation is scheduled along with streams. For example, here the add operation is associated with the store stream C, with two load streams as the operands. The hardware will decide whether to execute the stream locally or at a remote bank, depending on the locality. Here, if stream C is offloaded, the computation will also be performed remotely. To see how this can lead to a general solution with new opportunities, here we compare a conventional system with near-stream computing in three common cases. When reducing over an affine access to array A, a conventional system needs to fetch the data and perform reduction at the core. While in near-stream computing, the reduction is offloaded with the stream, and only the result is sent back to the core. This reduces the request traffic, and there is no data traffic at all. For operations involving multiple affine streams, instead of fetching all arrays to the core, we can offload the streams to the LLC, with operands forwarded to the consuming stream and operation performed in place. This reduces data traffic, and there are no writebacks at all. Another interesting case is a read-modified write operation on indirect access B of A of I. A conventional core would first fetch array A and then compute addresses and access array B. In near-stream computing, the indirect stream can be offloaded along with the affine stream and directly generate indirect requests in remote banks. By doing so, we can reduce request traffic by decentralizing address generation and eliminating writebacks. Overall, we require less data traffic as we schedule computation near data and the fewer control overhead since we offload at stream granularity. Fully exploiting these benefits requires solving several key challenges. The first one is to make near-stream computing programmer-friendly, requiring no manual programming while still providing sequential semantics. To achieve this, we introduce ISA extensions to explicitly embed streams and compute dependencies, with full compiler support to automatically transform the program. Also, to efficiently execute near-stream computation, we introduce stream computing SMT context to each core, which are lightweight threads with no LSQ and limited ROP entries. This helps reuse existing hardware units to flexibly execute computation near data. Finally, frequent synchronization eliminates the benefits of offloading, and we propose range synchronization to dramatically reduce synchronization overheads. It only synchronizes every few iterations and checks alias against the ranges of touched addresses instead of individual cache lines. Combining these three features together will make near-stream computing fully cover the triangle of transparency, synchronization efficiency, and generality. We evaluated near-stream computing against two state-of-the-art NDC baselines using the LVM compiler and the Gen 5 simulator. Overall, near-stream computing reduces network traffic by 76% and achieves 2.13 times speedup over previous advanced NDC techniques. To summarize, we leverage streams as the new offloading abstraction to enable transparent, general, and efficient near-data computing. As the system scales up, we believe that the key idea of exposing rich access patterns and compute dependencies to hardware via ISA is critical to enable programmer-friendly near-data architectures. Thank you.